much. So before I go on and embarrass myself saying absolutely nothing about consciousness, I wanted to credit my authors on the actual science behind what I'm going to say, which is not about consciousness. So all of this is based on experimental work and discussions by with Peter Skorupski, Mark Rogram, Olli Lukkola, Tim Perry, Luigi Barcelona, Cyril Lamtamins, and our nonsense. So it's very bold of the conference organizers to invite me to speak about a topic that I've never published about, nor actually thought very hard about. So it's a little bit like Obelix being asked in an experimental theater to act when he has absolutely no idea what to deliver, and he's actually asked to deliver the final message of the play. So this year is me at breakfast yesterday. So as the performance comes up, I've just been given the cue to start speaking here. I don't make it sound hand-flappingly nervous. Of course, and here he marches forward to the stage. Say something, come on, anything, whatever comes into your head. And then what I usually do is insult the audience, and the whole thing results in a proper Twitter shitstorm and so on. But today I'm not going to do that. The scenario about consciousness is going to be a little more like this. So what I'm not going to do is define consciousness, because I'd be in very shaky territory there. Nor am I going to claim that bees have consciousness. But I'm going to talk you through a number of phenomena that have been discussed in the context of consciousness in other animals. So what I'm not going to engage with is what lots of people in comparative cognition like to be doing, which is claiming that their own pet animal is the cleverest one on the planet. And so you find all of these wonderful things like this. Actually, I'm responsible for this press coverage here, where bees have been fun to count landmarks, and this means that bees, in terms of math skills, are ahead of most American high school. This, by the way, the American comedian wrote this. Anyway, so that's what we're not going to do. And so, in the process of that, we're not going to, I think, in this talk, replace in this presentation the old worldview where there was a sort of evolutionary tree that automatically placed humans at the top, to replace that with an equally flawed worldview where everything suddenly becomes equal, because as Baerends says, there is a bit of a tendency for people to play with words and then see if they can somehow make their animal qualify by definitions, and then indeed every animal can do pretty much everything. Now, there is, I guess, a pervasive view that bees or insect brains in general are too small to do anything clever. And that, I think, is probably not so bee brains are small compared to certainly humans, not compared to flies actually, but compared to most mammals, of course, with fewer than a million neurons. So here's a bee brain, if you haven't seen one yet. So that's a frontal view of an insect head. And here are the three visual ganglia, lamina, medulla, and lobula. Here are the antennal lobes, so principal relays of olfactory computations, and these things up here are the mushroom bodies, which function in bees, at least, in multi-sensory integration and the sites of learning and memory. Now, so these brains are relatively small and relatively few numbers, but I think it would be well, not a good idea, to put it mildly, to say that therefore bee brains are simple. So of these 850,000 neurons, here's one of them. Okay, and so this is a cell identified by Martin Hammer in the 19s in Randolph Menzel's lab. This cell essentially functions as the olfactory, as the reward pathway in olfactory learning. But you can see that's a very complex structure. Not all neurons in a bee brain are this complex, but it's certainly Well, I think there's often an idea that a neuron is sort of a single item, a switch or something that either has or doesn't have a single state, and then perhaps with 850 cells, 1,000 cells, you couldn't do all that much. But of course, there's a lot of computation that can go on with a few 100,000 cells that have essentially the structure of a fully branched tree. Now, even a fruit fly, fruit flies might have as many as 10 million synapses between nerve cells and a few hundred different types of neurons just in their visual system. Now, is any of this prohibitively simple or too small for consciousness? I don't think so. I'm not going to, as I said, define consciousness, but Maurice Shanahan, for example, has essentially modeled phenomena like predicting the outcomes of one's own actions, in this case for robotic solutions. This wasn't actually designed with a view to generating a minimal neural network model, but with 40,000 cells in that simulation, you could certainly model this phenomenon of, for robots, for example, predicting the outcomes of their own actions. So 40,000, you could stick that in a bee brain quite easily, and you probably wouldn't notice much of a difference in gross neuroanatomy just yet. So I certainly don't think that the argument that any brain is too small to have consciousness is a valid one. On the other hand, you can do a whole lot without any form of consciousness whatsoever. So there's been a lot of work over the last several decades of bees' clever pattern recognition skills. So people present bees with, so that they're good at associating visual stimuli with rewards because that's what they do at natural flowers all the time. They seek out flowers for their sugar and pollen rewards, and then associate signals of these flowers with the rewards contained inside. And so you can exploit that natural tendency of bees in experimental setups by giving them artificial flowers and present them with all kinds of different patterns where one's rewarded and the other unrewarded or penalized. And it turns out that bees are often very good at not just discriminating patterns that at a glance look quite similar, but also classifying them by common features and so on. That's been viewed in some scenarios as in the context of concept learning and so on and so on. Mark Roper built a number of models to explore how these pattern recognition tasks might be mediated by relatively simple means, indeed without actually seeing images. And so the models that he builds his artificial neural networks on are all based on very simple feature detectors in one of the optic ganglia, the lobula. They're called lobular orientation sensitive neurons, and you can see that they have maximum responsiveness at two angles separated roughly 120 degrees. There's also a third type of such neurons in dragonflies, but it hasn't been found in bees yet. Now, what can you do in terms of pattern recognition with such simple feature detectors? So here's a basic architecture of the model from the lamina to the medulla through the lobula, where these orientation-sensitive neurons are, and he connects these up with the Kenyan cells, the intrinsic neurons of the mushroom bodies. And now you might say that a good model should not just replicate what a bee can do, but also fail where a bee can't solve certain tasks. And so from these historic works of James Srinivasan and so on, there's some patterns that look quite difficult to discriminate at a glance that bees are reasonably good at, some which surprisingly, so these authors claim, they actually can't resolve, so that bees will choose roughly 50-50 when they're presented with these patterns. So I'll skip over that. So Mark tried a large variety of different ways of wiring up these lobular orientation sensitive neurons with the mushroom bodies, and then predicted how each of these models, how good it would be at discriminating a variety of different patterns. And so he simply correlated, as one does, the models predicted result in discrimination on the y-axis and the percent correct choices in the behavioral discrimination test as measured empirically. Now, what I guess everyone wants to see typically in such scenarios is that everything's nicely plotted along a line. So if you have a good correlation, then you think that your model's done something useful. That's not what happens. So by the way, all the different colors here are slightly different models, slightly different ways of wiring up the orientation-sensitive neurons with the mushroom bodies. What happens instead of us finding correlation where everything's lying nicely on a line is that all these super simple models actually perform better than the real ones. Practically all these dots are above the line. And so what this means is that many of these clever pattern recognition abilities that people have diagnosed in bees, you can actually get by without seeing images. These models are so simple as to be probably caricatures of what really goes on in a bee brain. There's no virtual little image floating around in the bee's head here. There's just two feature detectors wired up with the mushroom bodies in various ways, and you can solve a huge variety of pattern discrimination tasks better than the real bees do. Okay? So clearly in that case, even for what seems to be relatively clever pattern discrimination tasks, can be mediated without there being a need for image vision. And I guess also there is evidence from, in this context, interesting evidence from humans that, of course, some visual discrimination can be done without conscious awareness. So blind sight is the phenomenon that some patients who've had damage to their visual cortex and are blind in certain parts of the visual field can nonetheless make certain visual discriminations, even though they're unaware of them. Interestingly, this citation, I haven't looked up the original reference, but the claim here is that one such patient could distinguish horizontal bars in his blind field from identical bars tilted by as little as 10 degrees, which curiously is exactly what a bumblebee can do. So you can do clearly some visual discrimination without consciousness. And indeed, Fei Pang has modeled olfaction and various olfactory cognitive phenomena in the bee brain, again, not tweaking the model in any way to mediate or generate any kind of desired behavioral output, but feeding only neurobiological information into the model and asking what pops out of it. And with a very simple architecture in olfaction, even phenomena such as peak shift, negative and positive patterning, could be generated as pop-out phenomena from just a very simple architecture, three-layer neural network. So you don't need consciousness necessarily for many kinds of phenomena. Now, I've mentioned concept learning earlier on, and so here's one of the experiments by Aurora Vargas Weber and Martin Jorfa and so on, claiming that bees have learned a concept. And the way this works is that the bees are trained into a Y maze that has two arms, and there are two options, as always in a Y maze. And the bees here are asked to find arrangements of two stimuli, such as one of the stimuli being a referent, in this case a horizontal bar, and another stimulus, which can be a circle or a cross or a horizontal bar of a different color and so on. By the way, so there's no confusion, this central cross here just marks the center of the square here. And so if these bees are trained to an aboveness task, then that means that in panel 1 of these two options, this is correct because this side has a stimulus above the referent. Okay? In these two panels, the left side is correct because this has anything above the referent. In the third pair, this one's correct because there's that little cross above the referent. And in this final transfer test, the right arm is again correct because there is an item above the referent. And so what bees can't do, I guess, in this case is simply associate one pattern with reward, because the stimulus that indicates reward is always a different one. So here it's this radioactivity symbol, here it's an orange circle, here it's a yellow cross, and so on. So the claim, therefore, was that the only way for bees to solve this task was to somehow remember the concept of there being something above the referent. Now it turns out that there are a variety of, so first of all, for fairness reasons, that's exactly the same procedure that others have used for pigeons and primates and so on, and in those cases diagnosed it as evidence for concept learning. So the authors can't be blamed for departing from what's the convention in that field. But it turns out that there are a number of very simple ways to solve this task. And so Marie Guiraud and Mark Roper have done experiments to replicate this, but also ask, how do bees actually do it? And it turns out the way that they seem to be doing it, it has nothing to do with concept learning whatsoever. They choose the arm of the wire maze that they fly down. Let's look at an aboveness task. Okay, so let's again look at the scenario where this is correct, this is correct, this is correct, this is correct, because there's always something above the referent. So the bee flies randomly into the left or the right arm. Okay, then flies close up to the target and simply picks the lower of the two objects. So if the bee has randomly flown into the right arm, then she looks at the lower object, referent, fine, let's pick that one. Flies into the left arm, flies to the lower object, oh, that's not the thing I want, leaves and flies into the right arm. That's how bees seem to be solving it. No evidence for concept learning there, but a simple visual trick by which you use a movement strategy. Just fly to the lower of the two objects, check if it's the right one. If it is, stay. If it's not, go to the other one. Okay? So that's an alternative by which this task can be solved, and for fairness reasons, that might be how it might be solved in some primates as well, if you actually look where they're looking while they're solving the task. Now, that doesn't preclude us from making that task more difficult. Clint Perry, in collaboration with Andy Baerends, did just that. He explored whether bees have something like metacognition. Do bees actually know what they know? And the task in their case was made progressively more difficult. So they again had a horizontal bar as a referent, and then presented various other objects as alternative stimuli to be paired with this referent. And of course, if there is a big altitude difference with the above stimulus or the below one, then the task is relatively easy. But if they're close together, it becomes more difficult. And eventually impossible if they're actually at the same level. And so you can generate tasks that vary in difficulty. And in addition to giving them the option to choose right and left, these authors also gave the bees an option to just opt out and not make a choice and fly away. It turns out that indeed the bees, when the task was difficult, opted out more than they did when the task was easy. And in the process improved their overall record of correct choices. So they seem to be, if you take that, take this opting out frequency as evidence for knowing what bees know, then they acted in line with the criterion required for metacognition. Another line of experiments that we've been using, because we're, in addition to sort of geeky laboratory type settings, are also interested in how bees learn in nature. And one of the things that bees have to learn about, in addition to flowers, signals that are rewarding or not rewarding, is about danger in flowers. And so these crab spiders hunt flower visitors in flowers, and actually some species have chameleon-like features by which they can adopt the color of the flowers on which they prey. And so we took this scenario into the laboratory to make it more controllable, and had two types of flowers that were either spiders that were either conspicuous, as in this case, or cryptic. And then we punished the bees by when they made an error by capturing them. Let's see if this works. So here's our flower array. You can see, so there the bee lands on a safe flower. That's just fine. And now this is a naive bee. She doesn't yet know what the danger is. That so the bee gets captured for 2 seconds. These are sponge pads, so the bee doesn't get harmed in the process. So I have to admit it took us a while to fine-tune the scenarios here. But the bees were just fine after that. So they were captured for 2 seconds. Here's the same thing as an image sequence, and subsequent release. And after some such experiences, the bees become quite careful at inspecting every single flower to see whether there's a spider on it or not, even if the spider is not distinguishable by color. And they're remarkable, so that obviously, as you might expect, for both cryptic spiders, so that's the yellow spiders on yellow flowers, and the white columns are white spiders on yellow flowers, so conspicuous ones. They get better with experience. They don't get as good with the cryptic spiders. Look at the yellow bars as they do with the white spiders. But they get reasonably good, and error frequency becomes low in both cases. But if you examine their scanning behaviors, the bees invest a whole lot more time when this is visit number, this is time spent scanning in front of the stimulus, and the cryptic spiders induce the behavior marked by the grey dots here, whereas the conspicuous ones, that's the bees faced with conspicuous spiders. So the bees scan longer if the spiders are hidden, and the bees know that they're hidden, and that even happens if you test them the next day, so quite a while after they've last been attacked. And interestingly, while the bees minimize their errors in landing on unsafe flowers, they essentially see ghosts. So there's a higher number of false alarms where bees inspect a perfectly safe flower and say, oh, that doesn't look quite right, and fly away. Okay? So make of that what you will, but certainly there's much more than a response that's directly induced by an unpleasant stimulus. So they change their behavior in the long term in order to minimize being captured by spiders. But this has one implication is this curious paranoid behavior that they're actually avoiding flowers, sometimes that actually don't contain a spider. Clint Perry took that a little bit further, and based on this and also work by Jerry Wright on emotion-like states in bees, faced them in a scenario where there are ambiguous stimuli, so that, for example, in this experimental setup, so here's one of our flight arenas, and there are 5 options of artificial flowers to choose at the end. And they're distinguished by either both their spatial position and their color, and the reward contained within them. And here, in a very simple scenario, say in trial 1, the bees experience a reward with violet on the left side. Then they're given a green stimulus. In trial 2, there's no reward there. And then they're given several options in between that are all rewardless, and then there's another reward in trial 4 on the left side and so on. So what bees know in that case is that essentially, this is the testing. So the training is just rewards on the left with violet, no rewards on the right with green. And during testing, they're given various intermediate options that are ambiguous, of course, because they're between the rewarded and the unrewarded option. And so the bee has a choice to decide, well, this thing is sort of in the middle, could be rewarding, could be unrewarding, glass half full, glass half empty. So they have to choose whether that is potentially a rewarding flower or not. And so they do. So here's the curve that you get for the rewarded option on the left, and the so this is the latency to enter. So they fly into the left option right away when they see it, and they take quite a long time to choose the right option. And all the other stimuli in between are chosen at intermediate frequencies. But the interesting thing is that if you give bees an unexpected tiny reward droplet where they've never had one before, that is in the tunnel while they're waiting to enter the chamber. So they don't fill up, they just get a tiny droplet of reward and then make the choice. Is that then the latency to enter the unrewarded option stays the same, but the intermediate options, suddenly the bees choose faster than if they had not received that surprise reward prior to this action. Okay? And so that in the vertebrate literature is valued as evidence for a positive judgment bias in this case, for when animals respond in such ways to intermediate options. And to then explore whether this is a more general affective state that affects other behavioral judgments, which of course is a hallmark of emotion-like states, Clint and Luigi then did further experiments where instead of giving bees options between ambiguous stimuli, the bees faced a predation attack of just the kind of nature that you've seen earlier with the crab spiders, that is, in the entrance tunnel while they're waiting to enter the experimental chamber, they suddenly get squashed by a sponge pad, as if they were under attack by a crab spider. And needless to say, the bees are typically a little bit upset if that happens, and are reluctant to initiate flower foraging right away. But interestingly, this depends quite substantially on whether prior to that adverse predator attack, again, they've been given that tiny sucrose droplet. If they've been given a sucrose droplet and then get squashed, then they return to flower foraging much faster than they do if that simulated predation attack wasn't preceded by a reward. So there seems to be this surprise reward seems to affect a number of behavioral routines, indicative of there being some sort of general effective state change. And we also found with pharmacological treatments that this is a dopamine-dependent response. Now, one paradigm that's been probably bees haven't been faced before visiting our lab ever in evolutionary history, the string pulling task, where in this case artificial flowers are presented under a glass screen, so they can't get to the rewards contained in the center of these flowers. And so in order to get there, they have to pull the string, which is a popular task in corvid cognition and so on. Here's the first bee that we ever tested in that scenario. So here she flies around a bit and then grabs the string and gradually pulls it out. And you can see it's not yet very skilled at this task, but it manages all right, and finally gets to the reward. Now, the vast majority of bees require a stepwise training procedure where we progressively put the rewarding flower further under the glass dish. But there were two individuals that solved it clumsily but spontaneously after having exposure to blue flowers that were openly accessible. So out of over 100, 2 individuals managed it spontaneously. But we were also quite fascinated to see that bees could quite easily learn these techniques from observing one another. So here's an experienced individual marked with the red dot, and a second individual that hasn't solved the task before. You can see that that second individual actually has no idea how to solve it, but it's quite keen to be next to the demonstrator and is simply at this stage scrounging on the demonstrator's efforts, and they're both now there sitting together consuming the reward. It'll be probably done in about a second or two. And then you can see they'll sort of start getting a little agitated because now the reward is all consumed. There's a limited droplet in there. And so the demonstrator will now move over to the next flower. This naive individual has no idea how the task works, so it just tries some more and sees that there must be something here. And meanwhile, the demonstrator has already pulled out the next flower and so on. You do that a few times, and the observer can do the task as well. Not only that, but even if you spatially separate the observers from the demonstrator, so you put the observers in a little glass box and they observe the technique, they can still learn it. Now, as a good Skinnerian, you can well argue that most of this can be explained by operant conditioning. After all, most of the bees that we trained were trained in a kind of shaping or stepwise training procedure, though there are some individuals that learned it spontaneously. And even the social learning, of course, can be explained largely by the bees being attracted to locations where they see other bees and then rummaging about in their own ways there, and then gradually figuring out the technique by simple operant learning. Possible, and that's how we largely interpreted it, but alternatively, you could, of course, put that into the class of problem solving and attribute some consciousness-like states to it.
Are there any data on whether bees do simple mimicry where there's no reward involved, just copying each other's behaviour parrot fashion?
I'm not aware of any such information. So lots of people, I think, when we published this work, first asked whether there's something specific, especially intelligent to social bees, and whether they're more clever at solving such tasks. I suspect not. I think many of the forms of learning that you find in social animals are exactly the same as you find in solitary animals, or at least rely on similar mechanisms, only that in social animals, of course, there is often the conspecific takes on a specific salience in driving such behaviors, but I don't think there's anything especially clever about solitary animals by default. Here's a video that Olli Lukola discovered at some point about, oops, sorry, do what I wanted it to do. Okay, I hate what I have to say. What you should be seeing here is, I have to do it anyway. What you should be seeing here is me clicking that arrow and then something happens. So here's there's a brick with a hole in it, and mason bees like holes in bricks and build their nests inside it. They're solitary bees. There's just one mum and her eggs and larvae that are getting provisioned. And then some nasty dude has taken a nail and stuffed it into the hole of this brick. If you Google solitary bee nail, you'll probably find it. And then, so that's a task that bee's never encountered before. There was no scope for learning it gradually. The bee lands on the nail and pulls it out. And tries various methods, including sitting on the nail and flying backwards and so on, but it eventually manages getting the nail out of the way. And again, certainly there was no prior exposure or training involved in this. The bee clearly solved this spontaneously, and so I'll leave it to you to judge whether that's a kind of goal-directed behavior or whether the bee knows what it wants to achieve and acts accordingly. Certainly, at least on short time scales, there is all kinds of evidence that insects can, to some extent, predict the outcomes of their own actions. And Baerends already mentioned reafference copies and the idea that you need to suppress the perception of the environment moving when you yourself move, and that's understood quite well, I think, on a neuronal level. Others have studied, for example, the neural mechanisms underpinning dragonflies chasing their prey in mid-air and so on. Now that's the immediate future predicted. I think it's very remote from me scratching my head and thinking what I'd really like to do in my retirement or something like that. So it's not, I think, the kind of time travel that is possible in humans, for example, but it's some predicting of the immediate future. Now, one behavior that we also studied, so in the previous string pulling task, the string was, of course, attached to the flower, so to speak, so in that sense it was a kind of obstacle removal still in the widest sense. In this task here, the bees have to use a kind of token, or a ball in this case, that needs to be moved to the center of this platform in order to obtain the reward that's made available underneath the platform if they've solved the task correctly. And again, there was some training involved, and the way this the technique worked if there was a human trainer was by mimicking a bee, which is shown here. So the bee first tries in the center, but there's nothing there. Here's a dummy bee that actually moves the ball so that the observer, the as yet naive observer, gets to see how it's done. And you can see that it's slightly hesitant about this observer, and it sort of opens its mandibles. But it's now found the reward. And if we do that a number of times, showing the bee how to do it with a dummy bee, then the observer bee will learn it too. But the best way to train an observer bee is with an experienced bee. So in this case, we've made the task slightly simpler by constraining the ball movements to these three channels, so to speak. And there are three balls here, one far away from the target, and the other two are closer. Here's our experienced demonstrator, and here's an observer. We've played a trick on the demonstrator to make sure that it solves the task in a suboptimal manner. Okay, three balls. The ideal way to solve the task to get to the center is to pick this ball and move it to the center. That's not what the demonstrator does, because what the demonstrator has experienced in the past is that this ball and this ball are glued down, so she can't move them. And so that's what this demonstrator bee's learned to do. She always flies to the furthest ball and rolls that one. And that's what, therefore, the observer bee gets to see. So here's how that looks. So the demonstrator moves the ball to the center, and then they both get a reward of sucrose solution. And now we put the observer on the spot. So the observer does that 3 times. Every time the observer gets to see the demonstrator taking the furthest ball and moving it to the center. And now here's the observer bee on its own the first time, and it spontaneously picks the closest ball and moves that to the center. So the observer does not simply ape the demonstrator. It doesn't copy the technique of picking the furthest ball. But it looks at the task and spontaneously picks a new solution that it's not observed before to move the closest ball to the center. And we were quite impressed by that. I think I've always been, so you might or might not be aware of the literature on cognitive maps in bees and other animals, and I've always been highly skeptical of the idea that bees indeed spontaneously find new shortcuts over longer distances, but this clearly seems to be an example of picking spontaneously picking the shortest spatial solution to the task. By the way, the bees observers even solved the task optimally if the ball was of a different color, so they couldn't simply use a sort of simple arrangement of get yellow to the middle or something like that. Even if the ball was black, they still picked the closest ball and moved that to the center. A bit more on spatial behavior. So there's been a lot of groundbreaking work by Nikki Clayton and so on what, where, when memories in food storing corvids, which before the winter period dig in all kinds of little morsels to retrieve them later, and it appears that they can later on remember not just lots and lots of different locations, but also how recently they've stored what in each of these locations. So that, for example, they'll retrieve the caches earlier that contain food that is more easily perishable, and also they retrieve with priority the better food, and so on and so you find actually the same kinds of memories in a study from the 1940s by a student of Tinbergen's, a guy called Baerends, who explored not a bee in this case, but a parasitoid wasp. So these are solitary animals that capture, and in this species, capture caterpillars. There are parasitoids that capture all kinds of things, but these capture caterpillars and use them, paralyze them, and then deposit them in their nests for their larvae to feed on the paralyzed prey. And uniquely, this particular wasp species builds multiple nests, up to 10, and provisions several of them simultaneously. And so that alone, to remember the nesting sites, is extremely challenging because they nest in fairly homogeneously looking patches of sand. So here's a bee, a wasp just sealing its burrow with a little pebble and brushing sand over it so it can't be seen. In a few square meters of sand, you will often find dozens of wasps, all with multiple burrows in the vicinity of each other. And you can't see them at all, where the burrows are, unless the wasp digs it up for you. So that alone is challenging, but they have to remember multiple of these locations, but also they do remember what they've put in where. So some if they found a really large caterpillar, then one big one might be enough to provision a nest. If they've only put in small ones, they know to put in more small ones. So they remember what they've put in, and also they provision them in the priority depending on which nest needs to be provisioned next. Which actually, not in quantity. Food caching birds are reputed to have thousands of caches. These guys have up to 3 simultaneously, but qualitatively it's actually the same challenge. And that's commonly used as evidence for episodic-like memories. I'm still slightly hesitant of, it doesn't seem to me to remember quite the same thing as to remember an episode that surrounded the event in a way that I can actually tell a story about it. Remember that time when it was raining really hard and I buried my food under that tree. But it's something close enough. Now, one behavioral pattern that's been discussed in the context of consciousness by Griffin and others is the honeybee dance. And I take it that some of you might not know how it works, so I'll explain it briefly. So honeybees, this behavior was discovered, or deciphered rather, by Nobel laureate Calvin Frisch, who's observed, was seen over there in his Lederhosen, looking at some bees intensively. And so he discovered that if you observe bees in an observation hive, so normally it all happens in the darkness of the hive, if you replace one of the walls with a glass pane, then on the vertical wall you can see bees performing these repetitive motor displays where they sort of run around in a figure 8 shape and do this sometimes for several minutes. And it had been known for centuries that bees display this behavior, and also that it seems to happen after they've discovered some good food. But what Calvin Frisch discovered was that there was actually meaning to this repeated motor displays. And here's how it works. So it's actually a communication system to inform other individuals of the hive, of the precise coordinates of the food discovered by the dancer. And the way it works is that the longer this central waggle run, so this element of the figure 8 display here, from here to here, the longer they display the central run, the further away the food that they've discovered. So roughly 1 second of waggle running straight ahead means fly a kilometer. So this duration of that waggle run indicates distance to the food source, and the angle of this central waggle run indicates direction. And this is how it works. In the darkness of the hive, this is on a vertical comb, the bees use gravity as a reference. And if they run straight up on the comb, that means to other individuals attending the dance, fly in the direction of the sun. Okay, up means fly to the sun. If the waggaran points straight down along the direction of gravity, so to speak, that means fly opposite the sun. Waggaran straight down in the hive means fly away from the sun outside the hive. And any angle in between means a direction in between. So in this kind of dance where there's a 30-degree angle to the right of the direction of gravity, that means two individuals attending the dance fly 30 degrees to the right of the sun. Okay? So there's a kind of symbolic communication system that is, however, entirely hardwired, or not entirely, but largely hardwired, that bees don't have to learn in its detail. And the reason that that's been discussed in the context of consciousness is, I guess, the idea that the dancer somehow addresses a spatial representation in the dance attending bee and so on. But I think that's probably only a stretch. But I'll come back to this idea. Sorry.
So it's just about this, maybe a stupid question. Do they always leave at the same time during the day? Because the position of the sun changes during the day.
Yeah. It's a very good question. So what that means is that the dance must change over the course of the day. So the normal response of the dance attendee is to follow the dance for some time, perhaps a minute or so, and then to fly to the source that's been indicated. And that's a good idea for one reason, because floor patches are ephemeral, so they won't necessarily be rewarding a few hours after the dance. But what this means, for example, is that the dance itself changes in the course of the day. So a food source that's due south will be 90 degrees to the right of the sun in the morning, and therefore needs to be advertised accordingly. It'll be in the direction of the sun in midday, which is when bees dance straight up, and it'll be 90 degrees to the left of the sun in the afternoon. So the display of that figure 8 changes in the course of the day with the position of the sun.
Is there circadian information then feeding in?
It has to be.
Yeah.
Mm-hmm. So the perception of time, I guess, is important in consciousness-like phenomena, which doesn't necessarily mean that it's all that is required. But interval timing has been described in bumblebees. This is from a little dispatch I wrote with Peter Skorowski about original work by Boisvard and Sherry in current biology. So what they did is they gave the bumblebees a reward so this is the time 0 is when the previous reward has been just sucked up, and then so that's when the timer goes on, and then the interval to the next reward droplet that the bees were given while they were waiting could be anything from 6 to 36 seconds, and the authors then explored the extent to which the bees were able to withhold their tongue extension before being given the next reward, which is indicated here with this green trace. And it turns out that bees' anticipation of the reward was indeed largely correct, so they usually tried a little bit earlier, shown here in this red trace, before the reward actually arrived. But the duration during which they didn't respond at all corresponded quite accurately to the duration they had experienced as being non-rewarded. So they could measure the interval between these events, which is I guess a somewhat different time measurement to what occurs in simple circadian time. Here's an interesting figure from Calvin Frisch's 1967 textbooks, in which he describes that some bees dance in the night and spontaneously indicate locations that they had visited on the previous day. So the central grey interval here is the date. Sorry for this being in German. So this is, in this hive, bees were trained to one location in the morning. So this is the southerly direction here, and during the daytime the dancers highly precisely indicated that morning location. So as you've noted, the course of this, and the azimuth of the sun changes in the course of the day. And so in the afternoon, there's a different location in the east, and bees then highly accurately indicate that location. Now it turns night, and during the night, a handful, or well, maybe 2 handfuls of bees were seen, observed dancing spontaneously. And in that case, of course, they can't intend for other bees to go out there. They've spontaneously retrieved that spatial memory. So here are some bees before midnight indicating that afternoon location, although there's quite a bit of wobble. And then in the early morning hours at 4 a.m., there were several bees that indicated the morning location before the sun was actually up. So they retrieved a spatial memory accurately without there being a current need to go to that source or telling anyone to go to that source. And in some strange way, in accordance with time, so that bees doing these dances before midnight indicated the afternoon source, and those that indicated it in the early morning hours did it for the morning locations. So there's an interesting interrelation between time and space there. Should I wrap up? So I'll skip over the face recognition. And so here are the mixed take-home messages. I think that given what we've said about our interpretation of visual pattern recognition and how it actually can be done in many cases in really, really simple terms, ways which don't actually require there to be representations of images. You can do quite a lot of pattern recognition with very simple feature detectors and with some clever movement strategies by which you analyze the patterns. But there are certainly many ways of visual discrimination that do not require consciousness. I also suspect that various other phenomena, such as, for example, a theory of mind, mental perspective taking, that other bee might know that X, is not required for something like the communication that occurs in the dance. But on the other hand, many elements of recognition that I've talked you through, including sort of time and spatial appropriate behaviour that qualifies, at least by the common definition accepted for metacognition, learning by observation and so on, do qualify by what certainly my primate colleagues or corvid colleagues will say, well, yeah, clearly that's evidence for consciousness in my animals. So I'll bounce that question into the room because I'm not giving you any precise view of my own, whether that constitute consciousness, because that's I feel uncertain on that territory. So you tell me. Thank you very much.